work.
Yeah, thank you so much. So, hello everyone. My name is Majid Sohrabi. Today I'm going to talk about genetic engineering algorithm, which we modified the classical GA to solve some combinatorial optimization problem. So the order of talk will be, I will talk about the literature review, motivation and inspiration. I will talk about the genetic algorithm and also the engineering section, which we added 3 different scenarios to the method, and the experimental setup and result, conclusion, and the future work. So first of all, the metaheuristic algorithms get back to several decades ago. And one of the very famous one is the genetic algorithm. And also we have several others, differential evolution and particle swarm optimization, PSO, which is inspired by the swarm intelligence of a population. It can be like some birds or some fish. And there are several newly introduced algorithms. So as you can see, there are different categories. So you can categorize these metaheuristic algorithms. As you can see, some of them are evolutionary computation, which will be the GA, which is like inspired by the reproduction of the genetic. And some swarm intelligence, as I said, like PSO, ant colony optimization, and so on. And some of them are inspired by human behavior, like TLBO, teaching learning based optimization. And some of them are inspired by physics. So, so I didn't mention here, for example, some algorithms are population-based, as I said, like PSO-GA, and some of them are single solution-based, like simulated annealing, which is the behavior of the cooling melted, for example, metal gradually. And it's quite interesting algorithm. So about the motivation, why genetic algorithm? Because it has the ability to search towards the solution space, and it can be adapted to changing the dynamics, and it provides heuristic search. It's quite a strong algorithm. But there are some problems with these algorithms, which are, for example, they need parameter tuning. It is not just because of being GA. Almost all algorithms has this stage, and they have computational complexity when the problem size increase, and they also have a problem which we call it premature convergence, when the algorithm is stuck in the local optimum. And it is stuck there until the end of iteration, and it's quite hard to find the global optimum. And this is more common when you have a huge size of problem. And crossover and mutation are random. This can be considered as a strength and also some shortage. And also the lack of the, thank you. The lack of the problem-specific knowledge. So these algorithms start randomly, and there is no knowledge about the problem. And also, let me mention, evolutionary algorithms or metaheuristic algorithms are very strong in solving the combinatorial optimization problems, but their behavior changes dramatically when the problem size is larger. For example, we are going to allocate 10 vehicles to some centers. So algorithm is quite strong. Let's consider you have 1,000 vehicles you want to allocate to some centers. So the search space is quite high. So about the inspiration and the real world application of our ideas are, for example, in genetic engineering, can be used for disease treatment, to treat some genetic disorders, or removing the HIV virus from the infected cells. Thank you again. And also changing the characteristic of the newborn, infant, for example, changing the color of the eyes of the infant and so on. And also in agriculture, you can use to have high yield crops. Sorry, I wrote, it's wrong, crops. Yes, sorry about this. And also the crops can be resistant to pests. And this engineering working in this way, you will identify some genes which are more informative, and you can use them in some sense to like, inject them or cut and attach them like crossover and so on. So genetic algorithm was presented by Holland in 1975, and the general steps of the algorithm is the initializing the population for any kind of problem. The problem can be binary, permutation, or even continuous, but genetic was presented for discrete optimization, but you can map them together. So as an example, how it works, for example, you want to use an algorithm which works with continuous values like particle swarm optimization, because in PSO, there is a movement of solution with some equation. You can say if you have the binary problem, you can say, okay, in cost function, you can say all values less than like 0.5 will be denoted to 0, and the above will be 1. So you can map the problem together to use different algorithms. So we generate the population, initial population randomly, and then we have a fitness function or fitness score, which evaluates for any individuals, and it is beneficial to compare like two individuals together, two solutions together. And also it can be used for selection process, for example, roulette wheel. And the selection can be different scenarios. For example, you can select the individuals completely randomly, or you can use roulette wheel or tournament selection. Actually, a roulette wheel use the fitness function. Also, it gives you some probability. Those have the better solution. It can be minimization or maximization. They have the higher probability to be selected for crossover and mutation. And for tournament selection, let's consider you have 3 or 4 different chromosomes. You select them, and based on these 3 or 4, you select which one has the better solution score for example, more operations. And 2 steps are crossover and mutation. In each iteration, the algorithm tries to generate more solution. So there are some examples of crossover, like single point crossover, double point crossover, and uniform crossover. So in the top right, we can see the example for single point. You select 2 parents, let's say randomly from the population, and then you generate an index, and then you try to substitute the, for example, right side. So as you can see, the first parent is yellow, the second is blue. After single point, the right part changes. So you mix 2 chromosomes together. And double point is actually you select 2 parents and you select 2 points separately, and then you just substitute the middle part together in order to mix them. And the uniform crossover is, it also has a simple idea. You again select 2 parents, and then you generate a mask matrix which contains 0 and 1. When it's 1, for example, it selects from the first parent. When it's 0, it selects from the second parents. As for mutation, there are different ways also. Here we have the example for swap mutation. You have only here 1 chromosome, and you select 1 index and you swap them. And also there is a big swap. I don't have example here because I didn't have the space. You just select 2 different, for example, position. It's not just with the next one. You swap them together. And also reversion mutation is actually, again, selecting 2 different indexes, and then you reverse the gene inside, like as a reversion. You write the genes in reverse. So, about genetic engineering algorithm. So as you can see, there is a flow chart for the idea we added. So the algorithm starts with an initialization, and then there is a selection, and then There is a termination criterion. If it meets, it goes to the end of the algorithm because we are already satisfied. If not, it goes to the crossover first, then it does mutation. And then first scenario comes, which is you find dominant chromosomes. For making crossover, this is separate than classical crossover. And another one is the directed mutation, not randomly. Again, we use the idea of the first scenario. We build the matrix. I'm going to tell you how this matrix comes. And the last one is the gene injection inside the horse population. So in the first scenario, finding dominant chromosomes, which are the most repeated genes. So let's consider we have 100 individuals or chromosomes. And in each iteration, we are working on 100 like a population. And then there is a parameter which we define, which is P, and you can tune it, it's set by the user. It can be, let's say, 100 population, we want 60% of the elite part, because after generating the population, evaluating, we sort them based on the problem maximization or minimization. The top part of the population is elite, so we just consider the P% of it, like 60%. And our task is to find some pattern inside this elite part of the population, which generates the best cost or best function score. So we have 60 individual. In this case, we generate a mask matrix. It doesn't matter about the problem, if it's a permutation problem, binary problem, or even continuous problem. Our mask matrix contains only 0 and 1, which means if the gene is informative, we put 1. If not, we put 0. Here is not mask, actually. Let's consider this is the P% of the population, which is binary task, like knapsack. We say, okay, the number of 1 here is informative, right? We say, okay, 1 repeated more than a threshold. The threshold is also a definition. It can be 80% of the P. So it iterated like 80%, which is threshold. So we fix it. This is, for example, dominant chromosome. Now here is 0. Here is 1. Here is 0. Here is 1. So for mask matrix, is it completely the same population as the P%, which contains 0 and 1? And 1 says it's informative, 0 is non-informative. There is a pseudocode for how to find the this informative genes or creating the mask matrix. And the most dominant one is the one who has the most 1 inside the mask matrix. So in this case, so we said in the first scenario, we are using this information to make a crossover. As you remember, in classical crossover, we selected 2 different chromosomes, for example, randomly, we mix them together. But now here we fix one of the parents. It will be dominant chromosome, and then we select some other chromosome, we mix them with this dominant one. We assume it's dominant. Maybe even it has the lower score in the current population, but we found this informative. The second one is directed mutation. So as an example, you can see this is the dominant gene. The one, for example, has the threshold of 85%. So we say this is informative gene, let's fix it. And this one is also greater than or equal than 80. We fix this one also. And we select any chromosome in the P% best, 60%. And then we just make a mutation on those which are not informative. So we keep this gene because we consider it a good solution. So as a typical behavior, when you're doing the optimization problem, One strategy is at the end, you mix the current population with the crossover and with the mutation, and then you calculate, or you already have the scores, you sort them, you select the elite part again, for example, 100 best, which is not always good because you always discard the worst population, but worst population also can be as good as good part of the population, because with a slight change, they can move from a bad solution or local minimum to a global one. So we are going to invest on this part. So again, we have those masks, which shows us which genes are informative and not informative in our elite part of the solution. Then we select chromosome from the worst part of the solution, like 1 minus p, 40% less. And then we select randomly from the elite part, we just inject the gene from the informative one, which are fixed, from the elite part to the worst population. And then we calculate the score, and then we see how it reacts. So as experimental results and setup, we have 5 different methods. One of them is GA, and another is GEA with scenario 1, which is the classical GA with GEA scenario 1. The third one is the GEA only with scenario 2. 3 is only scenario 3, and the full scenario is GEA. And our benchmark is VRP problem. This is one of the famous problems, vehicle routing problems. And as the parameter definition, for example, we didn't do Taguchi tuning method because it takes a lot of time. So the Taguchi in general, it gives you a table of the combination of the parameters that you have. Actually, it's a truncated table of combination because you cannot do always all the combinations together. And then it gives you the result based on the figure you get. You define which parameter is better. But the way we did is we selected a set of parameters on paper. We tried to run the algorithm, and then we tried to set these parameters inside of our algorithm. So to keep this consistency, we put the maximum iteration as 1,000, population size 100 for all the algorithms because they are genetic, and crossover rate 80%, mutation rate 10%. As for scenario, which is to select the p%, we selected 50% for scenario 1, for scenario 2, 50%, and for the scenario 3, just 20%, because it is more sensitive to, injection is sensitive to the elite part. And the threshold is 80%, which means inside the best part, if there is 80% like repetition, you just fix this. So, and also this part is very important because when you're conducting such an experiment, these algorithms mostly work randomly. So in order to show the robustness of your result, you should run the algorithm several times on a single instance, then you take the average of them. So for this experiment, we just run 10 times each algorithm on each instance, F1, F2, F3. These are the information about our problem. And the result comes out of the average of all the run. And we reported the best cost, worst cost, mean or average, and standard deviation of our result. And as you can see in the first 3 problem size, F1 to F3, all algorithms could find the optimal or nearly optimal solutions. And when the problem size is larger, genetic engineering algorithm and or single scenarios could do better. So in average, the GEA, I bold them. I don't know if it's visible from here or not. So these are bold, and it shows they have the better cost at the end. So here are the convergence of the algorithms from iteration 1 to iteration 1000. And because the scale and the number of iterations was high and the convergence was somehow close together, I mean, in terms of value, we just magnified the first, for example, like 30 or 50 iterations to show the convergence of methods. And you can see the legend here. And another type of behavior you can do for this plot is to just take a log from it. You can see, but you can see the separation of the plot, but it's not a good way to somehow show the convergence. So this is only for F1, F2, and F3. And here you can see the convergence of F4, F5, and F6. And also we plot the interval plot based on the 95% confidence level to show the robustness of the algorithms. And the x-axis is the algorithm, and the y-axis is the normalized STD. So, as the conclusion, as we saw based on the results we got, the GEA between all the other variants could like beat other competitors, and it also opens an opportunity for further research, and we could increase the quality of the algorithm in order to like extracting some pattern. The pattern extraction was quite simple, and we try to make some more complex and better analysis in future to extract the more optimal way to extract these patterns. But on the other hand, we should be careful because these algorithms, after some iteration, the population will look like each other, because and in this case, you will not change anything. You just do operations, and then the current generation goes to the next, to the next. And also among all these GA variants, GEA scenario 2 could do better than other scenarios. And this work showed the application of GEA on the real world problem, which is vehicle routing problem. And for the future work, we can do some maybe parameter tuning and study the parameters, and even we can work on a larger problem to see how the behavior of algorithm changes. And even we can hybridize GEA with some other methods like simulated annealing, which they are already in literatures. For example, they mix GA with simulated annealing. They replace mutation by simulated annealing. And in this way, you can use the advantages of both algorithms. And yeah, thank you. This is about my talk. And these are some references which I used. Thank you.
Okay, thank you, Majid. So, do we have questions?
Yes.
Welcome.
So thank you a lot for a very interesting talk. I have several questions. I have noted them. So first of all, can you go to the very first slide, like this title? Yeah. So for solving combinatorial optimization problem, what's the problem?
So there are several types of combinatorial optimization problem. In this problem, we used VRP, which is you have several centers and you have several vehicles, and you can
Vehicles, like
Vehicle road plane.
vehicle routing problem.
Routing problem.
VRP.
Vehicle routing problem.
VRP. This is a very well-known problem, and
first letter,
Is
can
V.
you decipher it like the full
vehicle,
like
vehicle means machine. Transport, yes.
Yeah. Okay. So it's some well-known mathematical problem.
Yes, it's completely well-known. And they have different variants, for example, with a lot of constraints.
And you choose some data set which is or benchmark.
We generated the benchmark, for example, different size. You have 8 centers and 3.
Yeah, you generated the benchmark compared to your multiplication with. Okay, so VRP. Okay, so yeah, and the question is, what's the is there a time complexity estimation for this approach?
So actually, these algorithms sometimes are quite fast, and also it depends on the number of iteration and number of population you select.
But yeah,
In a typical way, in this case, let me tell you, our algorithm, if you use all the parameters with the same as GA, it increases the computational complexity because we are adding more calculation, right? But on the other hand, if we come up with a good and efficient pattern selection, in this case, there can be a trade-off between parameters. You can reduce the number of crossover or mutation in the classical way, and then you have some computation in the engineering part, then it will be also somehow the same as GA itself.
But if you fix everything, every parameter, how does it depend on the, for example, the population? So is it cubic, depends on the logarithmic, or is it like known thing, like is there exact formula for that?
So it can be like calculated even. So let's consider you have 100 population,
Yeah,
and you say 80% crossover, right?
yeah,
You are selecting 80 chromosomes, you mix them together, so you can understand you are some operations which takes this much time. You say, for example, you have 10% mutation. In each step, you are selecting 10 crossover, 10 chromosome and make mutation, and you are double them. There is also another types of like considering the criteria as we have here. There is NFE, NFE as I guess, yes, number of function evaluation. For example, here in a iteration, you can write the NFE. Whenever you calculate the chromosome fitness one time, it increases the NFE one time. This is also a criteria to evaluate it. And also, but we didn't, unfortunately, analyze this. You can do even like CPU time and so on, you can report it in your table. But we had like limitation.
So there is potential to analyze time in the future work. So
Yeah.
to plot the dependency on the number of iterations, for example. Okay, and the last question, so as I understood, it's like iteration algorithm, and what happens to the previous generation? You remove it, or after the new generation is generated? What happens to the old one? Is it does it stay in the pool, or is it extracted from there and not looked up again?
So let me tell you two ways. One of them is you have the current population 100.
Yeah.
You have 80% for crossover and, for example, 10% for mutation.
Yeah.
You mix them all, you sort them, then the top is like the best one. Then you select the NPOP, which is NPOP is number of population, which is 100. You select only the elite part and discard all the rest. It goes to the next iteration. Or it can be another process, like just tournament selection, which is
so you
even
select
better.
the best one. So it might be the case that some individuals from the old population stay in the next iteration.
It depends.
Okay.
If their cost is not good enough, they will be discarded.
Okay. Okay.
But in tournament selection is different. They have a chance.
Okay, in the small comment, maybe there should be a bit more math, but you're limited in time, so
yeah,
some formulas would be helpful for me.
So I didn't
because
focus.
I'm new by it, I don't know about evolution algorithms, so it's a bit hard.
Yeah, so in general, the genetic has not very complex because it's like the behavior. It's not based on mathematical formula. And on the other hand, I didn't focus on the problem itself because there was no innovation in our problem. It was just a well-known benchmark. So that's why I didn't add the description of the problem.
Yeah, and you're limited in time, so it's understandable. Okay, so.
Okay, thank you. Do I have more questions? Maybe some questions from online auditory?
The chat is empty.
Okay, the chat is empty. Okay.
Maybe
Yeah, sure.
I remember that your research is inspired by some other work of Iranian researcher, maybe.
Yes.
Can you tell us a little bit who is that person? What is it?
So I worked some individual work with a professor from Iran. And we started to do some analysis based on some idea, but I developed this method. For example, the idea was very simple, but we couldn't get a good result. But here, we actually added the crossover to the first scenario, and in the last scenario, we did some more analysis. And in this case, we add some contribution in our problem. And even we mentioned my professor in ethnology.
Oh, in ethnology.
Yes.
Thank you.
Yeah, quite an amateurish question, but am I understanding it right? So you are comparing algorithms with this genetic method, and as a result, what do you get? Meaning we have some record that tells us in which points of data using we should use specific algorithm. Or I'm quite new to this stuff.
So if I understood you, I'm not sure, but you cannot use one algorithm to solve all the combinatorial optimization problems. So our task is to improve the GA itself, genetic algorithm itself. So in this case, when we are moving towards this direction, so there's a good opportunity to improve the algorithm itself and introduce this algorithm as a new version of like GA. Because as I said, when the problem size increases, even GA cannot solve it because the
No, I'm more just a practical problem in the sense that if I understand it correctly, we end up with some record which is sort of like sets of genes which we mutate, and at the end we have some something that we believe to be better. How do we use it with the problem? Like, what does it tell us where we should turn on specific algorithms that we mutated or something like that? I just don't get this simple stuff.
So actually each individual or each chromosome is a solution.
Yeah.
So you have different gene inside the chromosome. It goes to the cost function and it calculates based on the mathematics you have on your construction, right? And then you try to find the best solution, which is, for example, it can be a sequence. Let's say 5, 3, 4, 2, 1 is the optimal one. And you have a population which different sequence, you calculate the cost. And the goal is to find this sequence. And sometimes when the problem is large, the algorithm cannot go to find here or even be near this one. So our goal is to make some pattern to see, okay, there is a 3 here for the elite part. Let's put 3 here, like gene injection. 2 is here, let's put 2 is here, and do mutation in this part. Our goal is to reach to this solution, which is optimal or near optimal. Yes.
Okay, thank you. Okay, maybe the last question. Okay, actually, you provided some concrete values of parameters for your algorithm. And you also mentioned that some fine-tuning will be as one of the directions for the future work.
Yes.
Okay, in this case, suppose that instead of benchmark, you will be provided by some concrete optimization problem, some use case in biology or I don't know, in some types of industry. So in this way, do you have some methodology for fine-tuning of your algorithm?
Actually, for each different problem, you need to fine-tune fine-tune all the parameters. There's no a single solution. As a one method is a Taguchi table, as I said, you can create the table by Minitab, and you execute one time, you find the best parameter, then you set it, you run again, you get the result.
Okay, so thank you.
You're welcome.
So thank